and I'm a science writer. Well, it's just been recently that scientists have realized that actually viruses don't just make us sick. They can actually sometimes end up in our genomes. In other words, a virus sort of pastes itself into our own DNA. And if that DNA happens to be in an egg or a sperm cell, it can get carried down to the next generation. So that virus DNA goes along with our own DNA, and it's in our kids. And this happens actually incredibly often. Maybe not to everybody in every generation, but if you go over millions and millions of years, it actually happens so often that we now have maybe 100,000 pieces of virus DNA in our genome. And if you add it all up, it's huge. So about 1.2% of the human genome is made up of genes, things that encode for proteins, the stuff that we consider us. There's about 8.3% that's virus. In other words, we're probably about 7 times more virus than we are human genes, which is kind of a weird way of thinking about yourself. So if you're looking for your own idea of your own identity, you know, the human genome may not be the best place to look for it. You're just going to end up looking at a bunch of viruses. Now, a lot of those viruses, once they get into the genome and they go down through generation after generation, they mutate, they get crippled, they can't make new copies of themselves after a while, and then after a while a lot of them are just dead. They're just sort of filler. But there are some cases where our own genomes over millions of years have actually domesticated some of this virus DNA. So what happens is that there's a mutation to one of these virus genes, and it starts to switch on and actually make proteins that we can use. So for example, ironically, there are some proteins from viruses that will help cells defend against invading viruses. So we've basically taken these viruses in and we're using them as kind of guard dogs to keep the wolves out, because they will make proteins that will block receptors that these viruses might use to invade our cells. Another way that viruses have become a part of us is when we're all embryos in the womb. Before we were born, we were sitting inside of our mothers, and there was this nice placenta that was giving us food. The attachment where the placenta connects to the mother's body in the uterus has some very special proteins that create the right kind of barrier to support the placenta there. They're essential. They're called syncticin. And these proteins come from viruses. If you knock those virus genes out, say in a mouse, in an experiment, that mouse cannot have babies. Its placenta won't develop properly. So we really depend on viruses for our complete survival. So one of the big challenges now is to figure out just how many viruses there really are in the human genome. So far, the estimate is 8.3% of our genome is virus, but it actually could be a lot higher. The problem is that over millions of years, the viruses in our genome mutate more and more, so they look less and less and less recognizable as viruses. And so if there was a virus that infected our pre-mammal ancestors like 250 million years ago, which it probably did, we can't see it because it just looks totally random now. So it's hard to work back that far in time. Our view of things gets fuzzy. I mean, that's true of evolution in general, and so it's also true of this fossil virus record. But the surprising thing is that a lot of different viruses can get into our genome, and that's actually a big surprise. It used to be thought that only a certain kind of virus could get into our genome, and it's called a retrovirus. And that's a virus that might be HIV, for example. That's an example of a retrovirus. And all these retroviruses replicate in the same way. And what they do is they make copies of their genes and insert them into our DNA. So they actually splice them in there, and then our cells churn out all these new viruses, and then the cell dies, and the viruses go on to infect other cells. So that's retroviruses. And so you could see how a virus could get into your genome. I mean, that's what they do in general. So if they just happen to get trapped in there and then get passed down through the generations, you get viruses in the genome. But now it turns out that you can get other viruses in the genome. So, for example, the first non-retrovirus that scientists have found in our genome is something called bornavirus. And this is actually very weird. So bornaviruses, you probably haven't heard of them. The reason is that they may or may not infect people. They mostly are known in mammals. So, for example, they can make horses sick. They get into these horses' brains and they do really weird things. The horses go running around in circles, or they might bang their head against the wall of their stall until actually they crack their skulls or they starve themselves. It's really horrendous. And some people have actually suggested that schizophrenia and some other psychiatric diseases might be connected to bornavirus, but it's still very mysterious and controversial. So bornavirus is not a retrovirus. It doesn't actually insert its own genes into our cells. What it does is it just hangs out near our DNA and uses some of the molecular machinery to copy itself. That's how it works. Well, it turns out that there's bornavirus in our DNA. We have bornavirus genes. We're part bornavirus, which is weird. But apparently, our cells and our genomes, in a weird way, may actually be grabbing these viruses, grabbing genetic material from the viruses that are infecting it and pulling them into their own genome. So we may be sucking in all sorts of viruses, and we really don't know the full range of them. Maybe we've got flu virus inside of us. That's a possibility. Maybe we're part flu. We have this problem with fighting viruses. The problem is that really the only kinds of ways we have to deal with viruses are old school. So vaccines, for example, are very effective, but the first vaccines were invented in the 1700s. So we're talking about technology that's over 200 years old. Another good way to fight viruses is for having people wash their hands. That's actually slightly younger in terms of technology. That was in the 1800s that people figured that out. But still, we're talking about stuff that's over a century old. So scientists are looking for new ways to fight viruses. And one possible way that scientists are looking into is to basically turn the virus's own strengths into weaknesses. Now, the reason that viruses are so hard to fight, the reason, for example, we need a flu virus every year, is that they evolve very fast. When you get sick with the flu, you get infected with flu viruses, and they make lots of new flu viruses. But those new viruses are not exact copies of the old ones. They have mutations in them. A lot of those mutations are harmful. They just kill the virus, but some of them are beneficial. So, for example, they might make it difficult for our immune systems to attack them. And so those flu viruses that can evade our immune systems, they're the ones that take off and they dominate the population. And then there are new mutants and new ones and new ones and new ones. And natural selection keeps driving the rapid evolution of flu viruses that we have a hard time grappling with. Well, there's some research that suggests that viruses like the flu are really actually kind of at the razor's edge when it comes to mutation. They're mutating so fast that if they mutated much faster, they would actually develop a lot of harmful mutations that could slow them down, cripple them, and eventually literally drive them extinct. So the thinking is that maybe we could give people drugs that would speed up the mutation of viruses. So you get sick with the flu, and your doctor says, here, take this drug. It's going to speed up the mutation of those flu viruses inside of you. It's not going to harm you. It's not going to harm your mutation rate. We're not going to give you cancer here. We're going to attack those viruses. And so the viruses start mutating faster and faster. They get more and more harmful mutations, and then all the flu viruses in your body, the whole population just goes into the ground. It just becomes extinct. So scientists can make this work in dishes with cells. And there's even some suggestion that this may be how some antivirals actually work right now, and just people haven't realized it. And so scientists are trying to take that the next step, and so they're developing this method, which is called lethal mutagenesis, to apply it for example, HIV. So there are going to be some clinical trials starting to test out some of these drugs to try to drive HIV extinct within people's own bodies. I think we've actually already taken control of human evolution to some extent. We've actually changed the rate of human evolution just with our own activity. You can go back to the invention of agriculture, for example. So all of a sudden, people who could digest certain kinds of foods because they had certain kinds of genes were going to be at an advantage over people who couldn't. And you can see this in the human genome if you look, for example, at milk and people who can digest it and people who can't. So lactose intolerance that a lot of people suffer from, you find that in people who descend from ethnic groups who did not traditionally raise cows. Whereas if you look in some populations in Europe where they raised cows, or the Maasai in Africa who were cattle herding people, you can actually see the mutations that have allowed them to digest milk as adults. I mean, everybody can digest milk when they're little. I mean, that's what makes us mammals. But evolution has led to some populations of people being able to digest milk without much trouble when they're adults as well. Now that was thousands of years ago. So basically we have been controlling our own evolution without realizing it for thousands of years. And I think that we're only going to continue to alter our own evolution even more in the future because we're interfering in a good way with nature. So medicine, for example, medicine allows people to live who would otherwise die. So antibiotics will let people survive infections that they might be otherwise very vulnerable to. And even little things might make a big difference. So I wear eyeglasses because my eyes aren't particularly strong. Before there were eyeglasses, someone at my age would probably not be good for much. I wouldn't be a very good hunter without these glasses. I'm not a very good hunter with these glasses, but I'd be even worse without them. So that would put a crimp in how many kids I could have. So all of these medical advances have, at least in some parts of the world, blunted natural selection. Scientists call it relaxing natural selection. And so that's going to continue in the future, at least as long as we have medical advances and the quality of life improves around the world. But that being said, there are lots of ways that natural selection is just going to keep changing us. So for example, there's still plenty of parts in the world where people rarely, if ever, see a doctor, where there are lots of serious diseases like malaria or HIV, and so people are, in a sense, at the mercy of these pathogens, and if they have the genetic wherewithal to be more resistant to these things, they'll be more likely to survive than others. And that's natural selection right there. So that's going to be happening as long as we have this horrendous inequity in the world, where billions of people can't even get clean water, where they don't get much medical attention. On the other hand, even in a place like the United States, natural selection is going on right now. So, for example, there was a study that scientists did of a town in Massachusetts called Framingham. And it was just a medical study. They wanted to track people's health over decades. And so there were thousands of people in Framingham, and these doctors just took all their vital statistics year in, year out. And when a new generation was born, they started looking at those people as well. So they have this generation by generation record of how many kids people have and their health and so on, and they can look to see, well, what kind of traits are shared by parents and their kids. And they can actually see that the new generation in Framingham is a little bit different than the old generation. In other words, certain people in Framingham had genetic traits that made them a little bit more likely to have more kids than the others. So, for example, the women in Framingham are a little bit shorter on average than their parents were. And there are lots of other traits that are becoming a little more common. And so you repeat that and repeat that and repeat that in the future, and that's natural selection happening as well. So synthetic biology is, in a way, a very new kind of science, and not so new in another way. In the late 1960s, scientists were figuring out sort of the basic molecular workings of life. And they were understanding it so well, particularly in little organisms like E. coli and bacteria, that they said, you know, we might be able to actually engineer living things. And so the first really spectacular example of that was with E. coli. What scientists did was take a gene for insulin, for human insulin, the kind of insulin we make in our own bodies, and inserting that into E. coli. And so now you have E. coli with this gene actually churning out human insulin. And so a lot of diabetics today actually get their insulin from E. coli. It doesn't say E. coli on the box, but that's where it comes from. So that went by the name of genetic engineering and basically gave rise to the whole biotechnology industry, which is about an $80 billion industry today. So more recently, scientists have said, maybe we can take this further. Rather than just sticking 1 or 2 or 3 genes into a host microbe, for example, you know, maybe we can tailor entire networks of genes that can do really sophisticated new things. And so what they're trying to do is they're trying to think about E. coli or any other microbe or cell as kind of a network, in the same way that you could think of the circuits in a cell phone as a network. And so they just take the point of view of an engineer, and they just say, I'm going to rearrange this network, I'm going to plug in new units and make this network work differently and do new things. Things that you might never imagine living things doing before. Right now, synthetic biology is still in kind of the science fair stage, I would call it. And actually, if you go to MIT, every year they have a contest for students. So these undergraduates get together and they say, hey, wouldn't it be cool if, for example, we could make E. coli flash in these pretty colors? Let's make E. coli that gives off rainbows of colors. Or let's make E. coli that gives off the odor of spearmint. Because normally E. coli smells pretty nasty. So let's make the nice-smelling E. coli. And it takes undergraduates a few weeks in the summer to do just that, which is amazing and a little scary, that even an 18-year-old has the power to transform life in ways that it has never been transformed before. The reason that they can do this all is because there are now these online databases of genes, and they're basically laid out kind of like you would look in a catalog of circuit parts, for example. And you can say, oh, I want that, I want that, I want that, and I'm going to plug them together to make them do whatever it is I want them to do. Now, we're going to go very rapidly from the science fair stage to the industrial stage. I mean, there's a huge amount of investment in synthetic biology now. One of the really spectacular possible advances is using E. coli or maybe yeast to make medicine for malaria. There's a very effective medicine for malaria that comes from a plant called the wormwood plant, which normally grows in Asia. The problem there is that it's hard to raise the plant and then isolate this drug from it. It's called artemisinin. It's expensive and it's slow and it keeps the price pretty high. So the hope is that scientists at the University of California, Berkeley are going to be able to program yeast by just plugging in genes from different kinds of plants to churn out a precursor of artemisinin in huge amounts. And then you can just take that and just refine it a little bit, and boom, you've got incredibly cheap drugs for malaria, which you could theoretically distribute around the world, or actually you could just take these yeast themselves and set up tanks of them in different parts of the world so you could have them churning out this medicine on site. Well, parasites are a huge menace to any free-living organism. For one thing, there are just a whole bunch of them. There are a lot more of those parasites than there are of us. So perhaps 4, 5, 6, 7 parasites for every free-living species. That's one estimate I've seen, although I bet there's a lot more. And so these things, these parasites, they're trying to use us and other hosts to make more copies of themselves. That's what they do. And in the process, we can get pretty sick or die. So any kind of mutation that might give us a little bit of resistance, might be able to let us evade these parasites, is going to be incredibly valuable. It's going to be strongly favored by natural selection. And so you can see the effect of parasites on us in lots of different ways. I mean, you can just go through the genome, the human genome, and see that the fingerprints of parasites there. They're all over the place. They have shaped genes that make our immune system better able to recognize certain kinds of parasites, for example. They have, in some parts of the world, they have made people resistant to malaria by making their blood cells harder for the malaria parasite to invade. And on the other hand, we have also kind of reached kind of an uneasy kind of a détente with some parasites as well. If you go to a jungle and look at the people who live there, and this can be in the jungles of Venezuela or in Central Africa or what have you, places far from medical care, people are loaded with parasites, particularly intestinal worms. But it generally doesn't harm their health all that much. And what's also interesting is that people in these parts of the world also don't have a lot of allergies. Whereas if you were to go to a city in Venezuela, for example, you would find people who have very few of these parasites but have lots of allergies and other kind of autoimmune disorders. So there is a theory that over the past century we have rid ourselves of a lot of these nasty parasites. I mean, nobody wants hookworm. But the problem is that our immune systems had evolved to be in a kind of a balance with these parasites. So they would sort of hold them in check, but they would not attack them too severely. And it appears that our immune systems have to learn to find this balance. But if we live a life that is, in a sense, too clean, our bodies don't learn that balance, and so we get thrown off, and we might attack some meaningless thing like a piece of cat dander or a piece of mold. And we totally overreact because our immune systems haven't been trained to basically calm down. So parasites have affected us on all sorts of different levels. Now, if you're a parasite, very often you don't just want to make your host sick. You actually have other things in mind. So, for example, there is a fungus that lives inside of ants. It's called cordyceps. Now, the fungus has to get from one ant to the next. And what it does is it's going to shower its spores down on healthy ants. Well, what that means is that it's got to get up above those ants. So how does it do that? What it does is it infects an ant. So a spore gets into an ant, and it sort of burrows its way in, and it starts to branch out inside of the ant. And if you cut these poor ants open, they're like, after a while, they're just pure fungus inside. But they're still alive, and they look pretty normal. They're going around their business. But eventually, when the fungus is ready, they get a signal, and they get this urge to climb upwards. And what they do is they climb up plants, typically trees or small bushes, and they'll go about 2 feet up, and then they'll find a leaf, and they will go and they will perch on the underside of the leaf, usually, amazingly enough, facing north by northwest. These ants, they're heeding this call that's coming from within them to do this very specific thing. And the reason they're doing that is because it's good for the fungus. So what it does is it puts the fungus up in the air above other ants. And now the fungus can get ready to spread. What it does is it produces a stalk that pops out of the ant's head. So this poor ant has this giant spike that grows up out of its head that's covered in spores. The fungus, meanwhile, is sprouting out of the ant's legs and abdomen and is attaching itself to the leaf. So the ant is now being cemented to the leaf. And the fungus is also hardening the exoskeleton of the ant. In a sense, it's making this very durable case, this shelter, kind of a house where it can live and where it can survive. And by being on the underside of that leaf, it's protected from rain, and it's protected from intense sunlight. It's in this perfect place for being a parasitic fungus. And now the spores from the ant coming out of that spike can shower down on the ants below and infect them and make them suffer that same horrible fate. Now that's just one example. I know dozens, there are probably hundreds of examples that scientists have documented of parasites manipulating the behavior of their host. Sometimes it's going from one host to another in the same species. There are a lot of cases where what the parasite wants to do is get from one species to another species. So, for example, there is a parasite called toxoplasma. It's very common in birds and rats and so on. Lots of mammals can carry it. But they are not the host where toxoplasma can really reproduce and produce the next generation of toxoplasma. That host, what's called the final host, is cats. So you've got toxoplasma in something like a rat, for example, and in order for it to complete its life cycle, it's got to get into a cat. And rats are very good at not getting into cats. I mean, that's sort of what they're on Earth for, to avoid getting eaten by cats. They have incredibly sensitive sense of smell, and if they get the faintest whiff of cat odor, they get very anxious, and they look around. They take evasive action. They don't want to get eaten. What's really remarkable about a rat infected with toxoplasma is that it looks totally normal, except that it's no longer afraid of the smell of a cat. In fact, sometimes when toxoplasma gets into rats, they actually seem to get a little curious. They say, what's this? This looks interesting. I'm going to investigate this. And so it appears that the toxoplasma is very precisely manipulating the rat brain, maybe by secreting certain kinds of chemicals, to affect its whole network for processing fear and other kinds of emotions. And so it may be making it an easier target for cats. What makes this really intriguing is that about a quarter of all people on Earth are infected with toxoplasma. We get it from lots of different places. So, for example, the soil is actually a place where you can pick it up if a cat has left its droppings in the area. This is why pregnant women are not supposed to handle kitty litter, because kitty litter may be loaded with toxoplasma. Now, if you get infected with toxoplasma, generally it's not a big deal, because what happens is you may feel a little fever, but then after a while you recover and you're fine. What's happened is that the toxoplasma has formed little cysts in your brain, thousands and thousands and thousands of cysts in your brain, and it's just hiding there. It's just hanging out. It's still alive. In fact, every now and then they might break out, but your immune system can sense that they've broken out and they attack them again, and they go back into their cysts. So there's this balance that we strike. The reason that pregnant women aren't supposed to handle kitty litter is because if the toxoplasma gets into their babies, that's when the trouble starts, because the babies don't have a mature immune system yet. So there's nothing there to keep toxoplasma in check, and so it'll replicate like crazy, can cause brain damage. It's not a good thing. So there we are, 1 billion people maybe 2 billion people with toxoplasma in their brains. And we know that it can affect mammal brains. And you know, the fact is that a rat brain and a human brain aren't all that different. In the really basic ways, they're quite similar. So is it possible that the toxoplasma is affecting people? It's possible. The evidence is really, I'd say it's pretty sketchy at this point, but it's evidence that can't be just dismissed out of hand. So, for example, people with toxoplasma have been reported to get into more traffic accidents. So does this mean that they're being more reckless, that they're not being as anxious as a normal human or rat might be? I don't know the answer to that. But the fact remains that we have these mind-altering parasites in our brains, and so I think we ought to figure out what they're doing. There are lots of diseases in the tropics that we fortunately don't have to contend with in places like the United States, and we should consider ourselves fortunate because some of them are really horrendous. A particularly horrendous one is called sleeping sickness. Sleeping sickness is caused by a single-celled organism called a trypanosome, and it looks like a little fluke or a kind of a flatworm under a microscope, but it's obviously much tinier than that. They are carried inside certain kinds of flies in Africa, and these flies will bite people, and they will inject these parasites, these trypanosomes, into these humans, who will then start to get sick. And they develop something called sleeping sickness, which, you know, not surprisingly, makes you very tired and run down. The real problem is that unless you treat it, it is quite fatal. And so it's a serious problem in, particularly in the belt just below the Sahara. Now, 100 years ago, it was quite a serious problem, much more serious than it is today, but it's been gradually eradicated from a lot of places where it was a big problem. It was eradicated through good public health, through treating people, and through trying to attack the populations of the flies to basically break the cycle of transmission. And it's worked in a lot of places. And this is a story that has been replicated with a number of parasites, for example, a parasite that causes something called river blindness. It's a worm that actually gets into your system and can get into your eye and inflames your eye and scars it until you're blind. That is being very nicely eradicated, and other diseases as well. Sleeping sickness was getting close to that kind of eradication, or at least being really driven down to very tiny levels. But unfortunately, the war in Sudan has given it a new lease on life. And so there have been, in the past 10 or 20 years, new flare-ups of sleeping sickness. And so it's a real testament to the devastation that war can have. It isn't just people being killed by bullets. It's also people being killed by parasites as well. About a year ago, I got this really interesting message from someone, an email from a graduate student. And she told me about reading a book of mine, Parasite Rex. And my book is all about how fascinating parasites are, how important they are, and just how intriguing they are. And at the time, she was trying to figure out what she was going to do. And in a sense, she said I had given her permission to be fascinated by parasites. She had always been intrigued by them, but now it seemed okay. And so actually she is now a parasitologist. And to express her gratitude, she said she wanted to name a parasite after me, which, you know, I thought was fantastic. The parasite is called Acanthrobium zimmeri. I'm sorry, Acanthobothrium zimmeri. It's a lot of Latin there. In any case, it's a tapeworm. And it's not just any tapeworm. It's a tapeworm that only lives in one species of stingray that lives off the coast of Australia. It's a tiny little thing, maybe about that big. You know, some tapeworms, like the ones that get inside of us, they get to be 40 feet long, horrendously long. These are very tiny ones. But to me, it's still special because it's mine. What was funny, though, was that after I had sort of gotten over the initial rush of having a species named after me, I started to think about it, and I realized, well, maybe it's not that special. I was at this meeting of parasitologists, including Carrie Filer, who named the species after me. And I was talking to her and another parasitologist who studies tapeworms, and she was talking about how she was going to name this species after me. And the other parasitologist looked at me and said, yeah, I could see how you'd name an Acanthobothrium species after him. He's kind of, you know, he's kind of tall, pretty slim. I said, what do you mean? Well, he said, you know, there's another genus that's very round and kind of fat. And, you know, so I named, you know, I think he said that he named it after her aunt or something like that because it just matched her body shape. And I thought, huh, that's interesting. And then they started like talking about all the different people that they've named species after. And you realize they're naming them after relatives and friends, people who live down the block. The problem is that there are just so many species. So these scientists who study these tapeworms have thousands and thousands of species left to name. They need thousands of names. Obviously, this is just a microcosm of the whole problem that scientists have in naming species. We actually only really know a tiny fraction of all the species on Earth. We probably know just about all the mammal species, but beyond that, we're still pretty sketchy. And actually, some scientists have estimated that maybe we only know perhaps between 10 and 20% of all the species on Earth. Actually, that estimate is a really ridiculous lowball, I think, because they're not taking into account bacteria and other microbes. It's becoming very clear that there's a colossal diversity of microbes out there that we haven't even started to catalog. I saw one estimate, one microbiologist told me that he thinks that there are 150 million species of bacteria, and there have just been a few thousand of those species named. So, you know, it's still great to have a species named after me, but you know, I think a lot of people on Earth could have species named after them once scientists are done with the full catalog, if they ever get there. We tend to think of our experiences just sort of happening to us instantaneously. So, you know, I don't think when I talk to someone that they are across the room and therefore there's a certain amount of time that it takes for me to hear what they're saying. We just think that everything happens in real time. But, you know, the fact is that we perceive the world through this organ, the brain, and it works a lot kind of like a telegraph. So if you were to send a message to somebody with a telegraph and you start tapping out your message, they're not going to get the message immediately. It's going to take time for all those dots and dashes to make their way down the wire and get to the other end. We have wiring in our own brains. We have neurons which work a lot like telegraph wires in some ways. They actually use kind of a biological set of dots and dashes. They have little spikes of voltage that we use to process information. So, if I see something, it takes a while for it to get from my eye into my brain, and then it takes a while for it to spread to different parts of the brain, and then for that information to get integrated in lots of different ways. The way that you can think about this really vividly was brought home to me once when I was talking to a neuroscientist named Michael Gazzaniga. And he just, basically all he did was he took his finger and he stuck it on his nose. And he said, what's interesting is that you feel your finger touching your nose and you feel your nose touching your finger at the same time. But the fact is that the signal from your fingertip had a lot longer to go than the signal from your nose. And yet they got to your brain and they felt like it was happening at the same time. So so your thoughts have this speed, and your brain has to deal with that speed, has to deal with that delay. Now, you might think, well, we should just have brains that work as fast as possible. So we should just have fast neurons and just to speed everything up. Because time is money, because your survival might depend on a fast signal. There's a problem, though, is that speeding up these signals doesn't come for free. So one strategy that we have evolved for fast thought, as it were, is to insulate our neurons. And this is actually something that is used a lot in engineering. I mean, if you don't want a signal to dissipate out of a wire, you want to insulate it. We insulate our neurons with sort of fatty molecules like myelin. Another thing you can do is you can actually take another trick that telegraph engineers first developed, which is to make your neurons thick. So signals will go through a signals will go through a fat wire quickly, faster than a thinner wire. Now, the problem is that insulating your neurons and making them fat is a big cost. It takes a lot of energy to do that, energy you could be using for other things. And not only that, but your brain is a pretty tightly packed place. If you were to double or triple the width of your neurons, your head might not be able to fit through a doorway. So evolution has come up with these wonderful optimizing trade-offs. Our signals work quickly in some neurons and slower in others. We've sort of found this nice balance to speed it up as fast as possible without making the cost too high. And the fact is that when I touch my finger to my nose, I actually don't want the signal from my nose to go too fast. I actually want the timing to make everything seem to be happening at once. So actually, sometimes you need to slow thought down a little bit in order for the world to make any sense. I didn't really have a conscious idea that I wanted to be a science writer when I was young. I loved to write. That's just what I did. But I would write stories or articles for the local newspaper, things like that. I also loved science, but it was just something I just did. And I didn't actually think about the fact that I might be able to write about science until I ended up with a job at Discover magazine, a science magazine. And I started working there and suddenly realized that I really enjoyed this. And I have loved it ever since. I mean, very quickly I discovered that I could get on the phone and talk with world experts on all sorts of different subjects, and they were amazingly generous with their time and would work with me so that I would understand their ideas and their work and how it tied in with what other people did. And so ever since, it's been just a fantastic way for me to learn about the world. In terms of the people who I try to model myself after, there are a number of science writers who I really respect, and certainly in terms of just writing really good nonfiction, there are people who came in the generations before me who you just kind of look to and say, yeah, that's good. For example, like John McPhee. There are certain books of McPhee's where you just pull it off the shelf and open it up and read a paragraph, and you remember what good writing is supposed to look like. Because every now and then I totally forget the whole concept of writing well. But someone like McPhee will remind you of doing it well. And McPhee, although he writes about a lot of things, he is in some ways a science writer. He has written a number of books on geology and other things having to do with science. So people like him really help to keep me going. I was very surprised to discover that a fair number of scientists have some very interesting tattoos. And the way I discovered this was that a friend of mine who was a geneticist was at a pool party with his kids, and he was in the pool, and I noticed on his shoulder there was this DNA tattoo. And I said, that's cool. And he said, yeah, well, what's really cool is that I've spelled my wife's initials in the genetic code. And I thought, well, yes, that is true geek love. But it got me thinking, I've seen a couple other scientists with tattoos, and I wonder, like, do other scientists have it? So the nice thing about having a blog is that you can just ask questions out loud, even kind of silly questions like, do people have tattoos? And I was particularly interested in scientists who love what they study so much that they actually engrave themselves with it. And I've lost count of how many tattoos I have been sent, maybe like 300 or something like that. And a lot of times they really tell amazing stories. So for example, there is a neurologist who sent me a tattoo she has of a special kind of neuron. It's a neuron that is vulnerable in Lou Gehrig's disease, which her father suffered from. And actually her father suffering from Lou Gehrig's disease was what made her a neurologist. And so this is not just some random tattoo. This is actually speaking to this deep passion that drives her science. And I like showing these on my blog because I want people to understand that scientists are very passionate people. I mean, after all, if you think about it, I mean, they dedicate their lives to studying things like neurons or tapeworms or chemicals, and they're very often not getting very much money for it at all. So it's interesting to get into their minds, and one of the ways to get into their minds is to look at their tattoos. Now, I myself have never had a tattoo, nor do I ever plan on getting one. If I was going to get one, I might imitate one of the tattoos that someone sent in. So Charles Darwin, when he was first coming up with his theory of evolution, had these notebooks where he would sketch out ideas of his. And one day he sketched out a tree, and basically this was a way of him saying, I think that life branches like a tree. I think that species are related to each other by common descent, the same way that branches sprout off of a tree. And on this notebook page he wrote this tree, and above it he wrote, I think. He was still working it out. And actually there's an evolutionary biologist who has this tattooed on her side. And it's pretty cool. Still, I have not yet reached the threshold where I would ink myself.